Bismillahirrahmanirrahim. Assalamu alaikum and welcome to the course EL239 Analog Integrated Circuits offered by the Department of Electronic Engineering at the Kennedy University of Engineering and Technology. My name is Hashim Raza Khan. I am an assistant professor at the department, and together we are going to study half of this course. So, half will be taught by Dr. Oscillators Narejo. So I'm just going through the topics that we are going to cover in this course through the syllabus, and that includes integrated circuits and its historical background and how does it morph into the modern semiconductor industry. Then we will look into the operational amplifier and its design. There will be some review material for the discrete amplifier designs, and then we will see how to design a good operation amplifier. And mind you, the entire course is about CMOS. We are not going to deal with the BJT. Next will be the frequency response, and we will see how does the behavior of a MOSFET change with the change in frequency. That is essentially what we are going to study with most of the common configurations of amplifiers and circuits. The feedback circuits will be discussed next. And last but not the least will be the oscillators that we are going to study. The recommended books that you can see, uh, most are my favorite. The textbook, Microelectronic Circuits by Cedrus Smith, I'm sure you are already familiar with it from your course of basic electronics. A very excellent book about analog integrated circuits written by Bazar Ghazavi. I would say any edition of Cedrus Smith after fifth edition is good enough. I've written sixth, but I think right now eighth or ninth edition is in print. And similarly, for the Zad Razavi's text, you can either use the first or second edition, which I think which is the recent latest one in print. This, may I say, is like a historic text, but a great text by Grain Meyer, a very popular book. It focuses equally on BJT and FET, and as I've already said, we will focus more towards the FET. Now, before going into the course details and things, I know it's a very testing time for all of us due to COVID-19. We are at our homes and we are now supposed to study without that typical class environment. This is how we are going to communicate through lectures. And I will try my level best to make this experience as easy and as fun for you. And if there are any suggestions by you, I would be glad to accommodate it and hear it. So please, anytime if you have any suggestions or comments or questions, do not hesitate from bringing it in forth. And these lectures, the drill that we are going to provide you with 3 lectures for a week, and then there is going to be a live interactive session over the net on Google Teams, etc., using those tools. And there you can ask all the questions. So I strongly recommend you that you go through all these lectures first before coming to that online class. Otherwise, there will be very little learning or absolutely no point in coming to that lecture without going through this material. So I think in a way it's going to be beneficial. Many of times the students they miss the class, they come in late, or they were not very attentive back then for any reason. But since now you have all those lectures in the form of a recording, you can hear it, you can rewind it and hear it and rehear it. So I think this is going to be in some ways a better experience. And trust me, you always have to accept the change. All changes are positive. Only then you will move forward. If you accept the change, if you can't change it. Anyway, so let's move towards the. So the first thing that we are going to study is a brief history of electronics. And I know what most of people think and say history is boring. It's just a collection of names and dates which has been put there to confuse us. But trust me, it's much more than that. Uh, we are going to through the history of electronics in particular, and this will enable you to understand a few things. It will make you understand about the causality. That is the principle behind the cause and the effect. How did a technology brought about novel appliances, applications, and systems? So that causality, the cause and effect thing will be much more clear to you through this journey. Also, we only see the inventions. There is a transistor, there are resistors, there are diodes and pentodes and many such devices. Okay, some scientists made it, some engineer invented it, but why? What was the need behind making such things? This is the question which is usually missing from our conversations and studies. So we are going to briefly look at it and try to develop an insight how to think about the inventions and the rationale. Also, whenever there is an invention, for most of the inventions, there is a time frame, there is an expiry date, and after that, that technology becomes obsolete and irrelevant, and mostly it is replaced by a superior technology. So, what makes a technology obsolete? So, the answer lies in its own characteristics, and we will see through it through some certain examples. And our industry, the electronics industry, or may I say the semiconductor industry, is the most unique industry in the world. And we would see how it is, what is its present state, and we will try to extrapolate the future based upon our study of the history and the recent historical trends. We will try to extrapolate the future and would try to guess about the future, what opportunities and threats and challenges does it lie? Because we are all, inshallah, going into the future, so we should be well prepared for it. And a very important thing that being engineers, I hope we are not only looking towards getting a job and getting a comfortable life. As engineers, it is our primary responsibility to think about innovation, how to make inventions. This is how the world has moved forward by the inventions and innovation and disruptive technologies which has been brought to the light of the day by the engineers. So, what is the thought process behind it? How can we be a part of that journey rather being just merely some consumers of technology? How can we create technology? What is the thought process behind it? That is what we are going to look towards in this. Right. So, right from the start, electronics, we must have studied the number of definitions of electronics. Most popular, which I've mostly heard, is that electronics is a study of electrical engineering which deals with low voltages. No, it is not true. If I connect a bulb with a battery of 1.5 volt, it does not make it automatically an electronic circuit. Anyway, to cut the long story short, the definition that I like about electronics and have discussed with a number of people is that it is a branch of electrical engineering that deals with the patch of electricity from non-conductors. For example, there is iron, there are, let's say, bulbs and fans and motors. All those have conductors for the passage of electricity, but there are certain devices in which the electricity does not pass through conductors, it passes through non-conductors. And why do I say non-conductors? Why don't I say straightforward the semiconductor? Well, this is where the early electronics began. So early electronics, it began in the 19th century. You have already read about some of the early electronic components. For example, vacuum tubes, they had their origin in the Crookes tube experiment, the discovery of electron experiment, and cathode ray tube experiment that we studied back in class 9 onwards. So those were based on thermionic emissions, and they were just being studied as a phenomenon back then. That the cathode ray tubes, all those emissions that goes in the vacuum. So the particles, the charged particles, the current was moving through an insulated material that is the vacuum. And based upon that, rectifying properties were discovered of the vacuum tubes. And based upon that, diodes and triodes and pentodes were made. Comes the question, why did they make diodes and triodes and pentodes? What was the need for it? So the need behind the diodes and all those devices that it was the late 19th century, 1890s, and so was the time when Marconi invented the wireless and radio. So there was a need for circuits that can process the amplitude modulated waves and do all the communication circuits thing. So diodes and triodes and pentodes were very much good. That's why the vacuum tubes were invented, and they were mostly used for wireless and radio communication. So that was the need of a circuit and the application. So had there been no wireless and radio, I think there would not have been diodes and triodes. At least the research would not have been very much accelerated towards them at that era. So at every point in time, whenever we have some discovery, some technology, there should be some end goal, some application for it. So this is what. So by the way, vacuum tubes, we must have heard about it during our text in on computer science and those as a historic relic. Is any use of a vacuum tube today? There are niche applications. For example, I can show you. You can find it on the internet. It's a audio amplifier by a company called Space Tech, and its price is $4,680. In today's currency in Pak rupees, I think we are talking about something like 700,000 rupees for an audio amplifier. And you can see it looks more like a term project. And if you would notice, there are vacuum tubes over there. So why is a company making such thing in this day and age, and who is going to buy it? So there are people who are called audiophiles, that is those who love music, and somehow the quality and the of sound and music through amplified through these audio amplifiers is what they believe is much better than anything that the conventional semiconductor industry has to offer. So they have a very good linear curve and they get a very good sound quality out of it. That's why they are still being sold at a very premium price. Magnetron from a microwave oven is another example of a vacuum tube based device. And the vacuum channel transistor, that is a cross between vacuum tube and transistor. That is, if you see the MOSFET, there is a source, the drain, and on top of the region between the source and the drain is the gate where the channel is formed. The current flows from the drain to the source through that channel when a voltage applied at the gate. However, here what happens is that the source and drain are far apart. What is in between? Yes, there is an insulator, a vacuum in between these two regions. And since now the distance on the transistors is getting very miniaturized and small, this distance is very, very small. And even if we apply a small voltage, for example, the gate from here, it would create a very strong electric field, that is the voltage per unit distance. So the high electric field would make the current pass from source to drain, and such devices have been made, but it's still more in experimental work. It is already a 6 years old article, and there are no commercially available devices yet in the form of solid state MOSFET based technology vacuum channel transistors. But there's still the work is being going on there. So that is the vacuum tube in the 21st century. You got the idea about the vacuum tube based circuits. So what about the solid state electronics? It started with the invention of transistor after Second World War. Okay, well, it's more than that. In the early 20th century, circuits such as this were used for radio reception. That is, it was a radio to receive AM circuit. A crude form of this circuit is what's shown here. And this is a working electronic circuit, as strange as it may seem. So how does that happen? Basically, I will leave it to you to study the integrities of the circuit for yourself. But very quickly, I'm going to explain this. That you see, this is basically iron pyrite spool's gold, and then there is a wire is attached to it. So basically, iron pyrite is not a good conductor of electricity, so you can say it is a semiconductor. This is a metal. So you see, there is a metal semiconductor junction. So there is a metal semiconductor junction. This wire, it works as an antenna as well as a tuning coil, and the signal comes into it. This is the diode connection which you see here. So this is the diode, and this is the diode physically which is present here. So whatever is the signal which is coming here is passed through this diode, and in the air the signal, the amplitude modulated waves appears like this. So when it passes through a diode in series, it means the diode works as a rectifier. So it's a half wave rectifier. The negative half of the wave is clipped, and we have just the positive half. And then there is some inherent capacitance, or you can add up a capacitance, which would smooth out the curve, and you would just get the envelope of the signal, which is in fact the modulating signal. So at the output of the circuit, the Vout, which is shown here, and you can connect a small speaker here. So what you can receive is actually the amplitude modulated circuit, which is being demodulated at this point, and that can be fed into a small speaker or a earphone, and you can hear the radio channels. So this was what being done at the beginning of the 20th century. It is called the crystal diode crystal receiver set, and this connection here, you see, this is the semiconductor, this is the metal semiconductor junction. It's also called the cat's whisker. So this was a solid state circuit being used at the beginning of the 20th century for inexpensive radio reception. And if we take our minds back to the beginning of the 20th century, there were no internet, there was no mobile phone, there was no TV, in fact. So the article, which was a fascination for everyone, was in fact the radio. So radio was all the rage, and instead of having very costly radios made up of vacuum tubes, you can create your radio for your own, or you can get a very inexpensive set of radio for yourself. Another important point for you to ponder over is that where is the power supply? Yes, it does not have any power supply. It just works on the ambient energy in the signal, and it converts it into the sound waves and music. In a way, it is also what you may nowadays call energy harvesting. And now let's look towards the evolution of transistors and integrated circuit. The MOSFET was invented before BJT, right after Second World War at Bell Labs. William Shockley and team, they produced the world's first MOSFET, which is shown here in the picture. But BJT gained popularity because the process needed for MOSFET was not very trivial, and therefore initially all the circuits were made by BJT. And you have the basic idea of how BJT and a MOSFET works. So it is very intriguing for the scientists. Just think about it. You are having a working relay or a working amplifier on a piece of silicon. So why don't you have another silicon piece which is bigger, and we accommodate two transistors over it, and even a bigger piece and four transistors. Alternately speaking, we can have a piece of silicon and we miniaturize the design of a transistor and accommodate more and more transistor on that silicon piece. So that was the idea, the premise behind the integrated circuits. And right from the very onset, once the silicon transistors were introduced back in 1954, people started working on the idea of integrating the entire circuits composing of transistors onto a single monolith piece. So by the late 50s, the earliest integrated circuits were created. And now let's look at not just towards the device, but the end use. Why do we need circuits in the late 50s? So you see the radio, it has reached all the far corners of the world. People love to hear from radio. And the other market which was coming into play is the television. So we need circuits that are fast enough, that are good enough to create radios and television. And that's what these transistors are for. So the earlier designs were analog designs, and Bob Widler, the Widler current source fame, he designed the first operational amplifier in 1963, LM101. In 1968, LM741 was created, by far the most popular operational amplifier. 555 timer, another landmark integrated circuits. 555 timer IC was created in 1971. And then people started making transistors, and transistors got more and more complex, and it started accommodating more and more transistors. And we have now a very large number of transistors possible to be accommodated into an IC. So once we have integrated circuits in the 50s, that is pretty much of the end of journey of history of electronics, right? No, it has just begun. So let's look at the electronics and what did electronics do? Once we had the technology, once we had the circuits, what were these circuits good for? So I've created this table, and you can look into it, and it will take you through a historic journey. So from 1910s to 1930s, vacuum tubes were dominantly used for wireless, radio, and telephony. 1939, the war started, Second World War, and from 1939 to 1945, vacuum tubes were used for military warfare, radars, cryptography, etc. By cryptography, we mean that's the science of decrypting the messages that is being used by one army for communication. So you encode them so other cannot hear it. So decoding those messages required a fair amount of computational power, and the machines to decrypt those messages were made using vacuum tubes, as well as some other uses as well. So the case for the usage of computers for computation was well established during the Second World War, and the world recognized the importance of computers in the next half of the century. So, from 1945 to 1950s, transistors were born, we know, and they were used for radios and computers. From 50s onwards, television. In fact, television was invented in 1932, but started gaining popularity right after the Second World War. So then the focus of the integrated circuits created from the transistors in the 50s up to 70s was for televisions and computers. So now we are into 70s. The situation is that the television and radio have reached almost all the major populations of the world, and people who can afford the radio and television have it. So it is on its path of saturation. It's not really saturated. The world market is not saturated for radio and television, but most it's on that path. And people need more and more entertainment. So if you have radio, the radio is transistorized and became mobile. You can take your radio with you and move around. So naturally, people started thinking, why don't we can hear some recorded music in programs on the go? So that was the birth of Walkman. And by the way, you have to go to the cinema to watch a movie. Why can't I watch it at home? So that was the birth of video cassette recorder, VCR, and VCP. If you ask your parents or elders, this was one of the main gift items that people visiting Pakistan from the land of our holy sites, Saudi Arabia and the Middle East used to bring along with Abu Zamza. So Walkman VCRs was all the rage then. Anyway, so in 1980s, we are now in 70s, and the focus of the electronics is to develop products for the market, such as VCRs and Walkmans and VCPs, and this was what people were buying. So then we had technology which can even further miniaturize circuit. The question remains, what should we create with these circuits that would entice general population? So there are computers in the world, and those computers are getting miniaturized with the passage of time, and because of the technology. So by the 80s, the technology has advanced so much that the computer that was about a decade or two ago used to occupy a big room was now small enough to be kept on a on a table. And that was the birth of personal computers that was made in 80s, or you must say late 70s. So the question comes, why would I need a computer at home? What should I do with a computer? So computers means serious business as offices. So at home, primarily people started using it for gaming, video games developed. And then there were consoles developed solely for gaming, such as Atari and Sega and Commodore and Amiga. All those companies popped up, they used electronics, and the video game industry was born. The personal computing industry was born. It was born in 1980s. Why not in 50s, 70s? Because the technology was not mature, and there were other avenues of uh, entertainment. And in the 80s, the technology enabler, the electronics, reached that peak where it was possible to make personal computers and video gaming at an affordable price. Then in the 1990s, people have now the personal computers at home and they know how to play games and they're enjoying themselves. But what's next? So in the 90s, the PCs they proliferated all over the world, even in developing countries. And another important aspect of life, that is communication, it took main stage. So we had cordless phones in the 80s, and there were mobile phones in the 80s, but they became the mainstream item in the 1990s. Why? Because in the 80s, mobile phones were prohibitively expensive, they were bulky and large. But again, as the technology is progressing, the circuits are getting smaller and smaller, and it was possible to make mobile phones smaller and cheaper in the mid 90s. So the 90s, the focus of the technology is to produce personal computers and mobiles which are better and faster at an affordable price. Also in the 90s came the trend of internet. because right from 70s we had computers in the world, and at a very large scale we had computers all over the world. So if I want to transfer data from one computer to another, I used to have floppies, but floppy diskettes, but it means they were very prone to error, and it was a slow transfer of data. So why don't we connect the computers? That was the concept of Ethernet. And some of the computers were connected. The basis of the Ethernet was made in 70s. But you could not have connected all the computers in the world back in 70s. Why? The technology simply was not there. The circuits were not fast enough. The electronics matured in mid 90s that it was possible to get those computers connected. So in the mid 90s, the internet was born, the computers of the world were connected together. And initially, it was a very slow sort of connection. It started with a connection something like 7 kilobits per second, 14 kilobits per second. The best modem at that time was like 56 kilobits per second. So that was the birth of the internet in the 90s, and in the 2000s, the trend from the 90s continued. We had internet and we need faster and faster internet. We have mobile phones and we need better and better mobile phones. In fact, the mobile phone has become a fashion item. Everybody must carry a mobile phone. It's like a fashion statement. Another trend is that when we have internet, okay, we can get lots of data, we can get lots of entertainment, and we have mobiles. So the confluence of the two, why don't we combine them together? And the 2000s were focused on having mobile, the high-speed internet, and all the entertainment on the go. So you see the technology behind it is all electronics based, but the items that were created were laptops, which were getting affordable in the 2000s. It started back in 80s, but it was very expensive. And with the passage of time, the laptop's price it fell down drastically. From the 2000s, laptop got mainstream, and the internet servers and the mobile phones they also gained popularity. So these were the fields that were the impetus for the electronics industry. So those were the fields where all the circuits were lining up. Okay. And then in 2010s, what happened in 2010s? It was just yesterday, may I say, because 2020, we won't count 2020. It was all wasted. It was all wasted due to COVID. So what happens from 2010s to 2019? Actually, electronics, the mobile phones, it became a smartphone. The connected devices, IoT, Internet of Things, that's all 2010s. And Internet, so once we have connected all the computers in the world, we have connected mobile phones. So why don't we connect the devices? And that was is the concept behind IoT. So IoT started in 2010. It hasn't reached its peak. There are many things in its acceptance, battery being one of the challenges, bandwidth issues, etc. But that was a trend that started in 2010s and it was a major driving force behind electronics. Also, electric vehicles, renewables, solar panels, wind energy. So these are the fields that are taking that took main seat in 2010s, and the electronics it was driving there. What would happen in 2020s? So I think now you can see it for yourself. 2020s means electric vehicles would go mainstream. Renewables will reach more and more people, and as well as the connected devices, IoT would be a big trend in 2020s. There are many challenges associated with all of them, but those challenges mean opportunity. So in the future, where is it going to be? It's there. For example, is 2020 is going to be great for radios? It's already matured. Is it going to be great for television? Very small niche market. We know yes, television has benefited with the recent advances in technology from the CRT big bulky boxes. We are into sleek screens, but the sizes where they are playing, there is not much innovation there. Connected devices, renewables, electric vehicles, mobiles, these are there. And now personalized electronics such as augmented reality, virtual reality, VR devices, AR devices, wearable electronics. This is my prediction for the 2020s. These are going to be the big trends. Why is it important to make such predictions? Because like it or not, you are heading towards future. You are going to work in future. You should know where does all those good opportunities lie. You do not want to end up in a field which has already destined to hit the wall. So that's why we have seen that what is the trend of the technology, and from there we can decide for our future that in which areas should I work for the future. That's why it is important to discuss the electronics technology's history. And based upon that, you see, we have made some predictions about the future. I'm not saying that this is for 100% true. Anything like Corona can happen in future and everything will be jeopardized. But let's hope for the best. And mind you, it was all about just for the civilian technology that haven't gone into the military or space, etc. Those fields have also benefited a lot from the technology. But let's keep it for another day for that discussion. The trend that we have observed with the miniaturization and integration technologies used for transistors was also observed by many people during their times. And one such person is Gordon Moore, who in 1965 observed the trend of integration being growing at an exponential pace for the past decade. And based on that observation, he made a prediction. And he said that by looking at the trends, we can say that the number of transistors that are possible to be accommodated in an IC will get doubled in every 2 years. So this is what he said, and he wrote that in a popular articles magazine. And but Gordon Moore is a very important person in the history of electronics. In fact, he is the founder of Intel, the most dominant company in the semiconductor industry. And he saw this trend that the number of transistors that will be available is getting doubled. So then he sat and asked himself, as if, okay, if the number of transistors is getting doubled, so what's the big deal about it? Here is the deal about it. In a computer back in 60s, if it is going to take space of a cabinet in a room, then if you want it to be accommodated into, let's say, a smaller cabinet or into something which is much smaller in size, then what is the impediment? What is the obstruction in it? So the answer is that it requires a number of transistors, and since the ICs of that day in the mid 60s does not contain those many transistors, so it is not possible to have smaller computer. But he saw that okay, if the number of transistors are getting double in every 2 years, so if I want to have a computer which is smaller in size, let's say equivalent to a small cupboard, then what do I require? It would require something to have about, let's say, 1200 transistors in an IC. And what he sees in 1960s is that they can only get 300 transistors in an IC. So by looking at that trend, you can see that if in 1965, let's say, these are just hypothetical numbers. So in 1965, if there are 300 transistors in an IC, then in 1967, it will be possible to have 600 transistors. And in 1969, that we can reach even 1200 transistors and so on and so forth. So he sat together with like-minded people and said, okay, what we can do is somebody is going to create an IC which is powerful enough to power a computer. And the entire computer would be reduced to a chip, to a single IC. So why do we let others do it? Why don't we start it? So he started this, and in 1971, Intel launched its first IC, its first microprocessor, Intel 4004. And if you look at this graph, you can see that it started all in 1971, and then for regular intervals, you see that newer and newer ICs were introduced by Intel. And altogether, it's like a curve around a straight line. And let me tell you, this is a semi-log axis graph. So if it is a straight line or semi-log axis, it means it's an exponential growth. So this shows that there is an exponential growth in number of transistors, and this creates more opportunities. You can have faster and faster computers, and it is very difficult for any other company. It had been very difficult for other companies to catch up with Intel, because if a company wants to venture into this field, it would start working to design an IC of 1200 transistors. And what you would see is that by the time they will get that technology in their hands, Intel has already moved to the next technology node where there are more number of transistors. So this is something that would always be a catch-up game from others unless they invest a lot of money in it. And this is why I think Moore's law is the single most dominant force in semiconductor industry, because no other industry grows at such a pace, does not have evolution at this rate. So just imagine if there is, let's say, a fan industry, and there is a factory set up by a person, then its production would more or less remain the same for the next 1 or 2 decades without any substantial changes in its entire production lines. But here, whatever production line you establish, its product will be good enough only for a period of 2 years, and then it will be superseded by better and better technology, and you have to update your plant. So it means if you are making a product, you have only 2 years not only to sell it, to make it a profit, to get all the return on investments that you have made for that factory setup, for that fabrication setup, and also you need R&D for the future setups. And then you have to make a decent profit overall everything. So it is a very cutthroat business. It is a very money intensive business. And this will give you a glimpse into this worldview as if why developing countries such as Pakistan, even India cannot afford to have modern fabrication plants in their countries. And subsequently we'll see it doesn't make much business sense either. So anyway, another aspect is that no linear trend or such exponential trend can continue forever. Yes, the number of transistors are getting doubled, and we have already crossed the billion mark about a decade ago. Now we are somewhere like many billions of transistors in an IC. So what's next? Where are we going to head from here? There are competing technologies which are being investigated as of now. For example, 3D ICs. 3D ICs mean that many of these ICs that are made instead of different packaging, many of these chips will be packaged in a single package, one on top of the other. That is what we mean by 3D ICs. Then there is quantum computing, very exotic sort of thing. It's a total paradigm shift. Spintronics, which looks at the spin quantum numbers of the electrons and use it as a relay, as a switch, but again, it's not a generic uh, device like a transistor. Carbon nanotubes based structure, graphene based structure is, I think, the most promising of the technology for the next growth cycle. So this is about the Moore's law, very brief one, I would say. Still, it took us about 6 minutes. But trust me, when I teach it in masters, it takes about an hour just about Moore's law and its repercussions. How does the CMOS technology progress at such a rapid pace? Actually, it is because of the miniaturization of the size of the transistor. Some serious efforts were made to reduce the size of an individual transistor so that more and more transistors can be crammed into a small area. So this is about this. This is called the CMOS process node. Once we talk about the technology of transistor fabrication, we are looking at the smallest channel length that can be fabricated in a particular technology. So here you see that in 1971, it was possible to make a transistor whose minimum channel length is 10 micrometers. And in 1974, it was possible to fabricate transistors that had a minimum channel length of 6 micrometers. So you see the transistor's size has decreased, not only the channel length, in fact, all the parameters decrease the size proportionately, and hence you have a smaller transistor. Once there is a smaller transistor, it means that more transistors can be accommodated in a similar space, and hence the number of transistors gets roughly doubled. So these are called the technology nodes. So every technology company, the semiconductor technology company, they strive to achieve the design and fabrication of a transistor with a smaller feature size. And these are the process nodes that have been moving on. That is 10 micrometer, 6, 90 in 2003, 65 nanometers, 2005, and so on. Right now, if we talk about in 5 nanometers, it is 2020, the year, and the best technology that we have today on this planet makes transistors of 5 nanometer process. Okay, one thing I would like to clarify is that beyond 45 nanometers, it's more like a marketing term now, and there is not that the transistor's channel length is actually 32 nanometers or 22 nanometers. No, it's more like a marketing term. And there have been other technologies which are called FinFET, gate all around FETs, etc. So we are not going into those advanced topics, but just to give you an idea, why does Moore's law work, how it works, and will it continue in future? So this will give you a hint that in future by 2023 we expect to have 3 nanometer, and by 2025 there will be 2 nanometers technology. The transistor size are decreasing, but it's getting extremely difficult to keep on moving the Moore's law. And time and again, people have said that Moore's law is going to end. And let's see how the future transpires for us. But for now, this is how the things have been moving. And just to bring these numbers in perspective, what is 10 micrometer? 10 micrometer is about 1/10 the width of a human hair. A human hair is about 100 micrometers in width. So even in 1971, the channel length was about 1/10 of a human hair. And just compare it with 2016's number, that is 10 nanometers. That is a decrease in length by 1,000-fold. So now we can accommodate a large number of transistors even on the tip of a human hair. Such is the dimension, so small is the transistor that can be fabricated, that becomes the most fascinating and mind-boggling technology, the most complicated, state-of-the-art, bleeding-edge technology on this planet, which is employed in the manufacturing of CMOS circuits. This is just to give you an idea as to what is the dimension of a human hair compared to a transistor size. So for example, a roughly 75 micrometer human hair is this much thick or wide, and this is when we talk about 0.18 micrometer technology. And let me tell you, 0.18 micrometer technology is almost 2 decades old. And in 65 nanometer technology, it is possible to accommodate about 40,000 transistors on the cross section area. So just imagine what would be. And 65 nanometers is again about 15 years old technology. Just think about 5 nanometers. What could be done on the circuit which is as small as the thickness of a human hair? So this is truly awe-inspiring. Now, quickly, we are going to go through the different sectors of the semiconductor industry. Actually, it's a long, complex supply chain which comprises of many downstream and upstream industries. So let's look into it very quickly. So at the right bottom lies the silicon wafer production companies. Those are the companies that produces pure silicon, because we require absolutely pure silicon for the production of silicon wafers, and that means we require a 9N solution. 9N means that it will take about seven nines after the decimal point, 99.9999%. That much pure. And the process is called the Choralski process. You can see more into it into some standard literatures. And now it depends. This is how it is made. That we have the molten silicon, and a seed crystal is introduced into it, and slowly it is rotated and pulled out of this molten silicon at a very slow rate. And then we have a cylinder-like structure. The diameter of the cylinder depends upon the rate of rotation and the rate of pull, etc. And typically there are 200 millimeters or 200, 300 millimeters wafer. Now even 450 millimeters wafer are in process. So it depends upon the foundry as to what is the maximum size of a wafer that a foundry can process. The bigger the size of the wafer, the smaller is the wastages in producing the ICs, and therefore it will be more profitable. But again, to have an accuracy over an area which is as large as 200 micromillimeters and 300 millimeters is fairly difficult. These are the companies that usually produce these silicon ingots. And these are basically European-based companies mostly. Once we have the silicon ingot, they are sliced and diced into thin wafers, we call them. So this is produced well, and then they do polishing. Resistivity of the substrate is managed. If there is a silicon on insulator option, so additional processing is done. Epitaxial layer is processed. Companies like Siltronic, Sunco, Sun Edison are the major players in it. Once we have the wafers, then we start with manufacturing, fabrication of the circuits for it. Now, there are some classical and new business models for it. For instance, typically there are companies that design and do fabrication all within their own self, all within their own companies. Companies such as Intel, Infineon, Samsung, these are called integrated device manufacturers that design the product themselves and fabricate it in their own foundries. But as you can see, a modern semiconductor fab would cost you anything between 7 to 12 billion dollars, and this is a very heavy capital investment, and the return on investment is pretty low because it would start becoming outdated in 2 or 3 years time. So right now, many of the companies, they are no more integrated device manufacturers. Earlier, who were integrated device manufacturers are no longer doing this. So have they gone bankrupt or are they defunct? No, they have changed their business model. For instance, if we see, there are companies which are called pure play semiconductors. So these are the companies who do not do any sort of design. They have concentrated on the fabrication aspect of the business. So all they have done is make foundries, make fabrication facilities, and people who want to have the designs fabricated, they contact them and provide them their own designs. Of course, there are non-disclosure agreements and they are very religiously followed. Otherwise, the penalties would be totally detrimental and disastrous for the companies to have. So TSMC and Global Foundries, they receive designs of others, make their designs and send them back, and they make the money out of it. Again, this is a very capital intensive business. TSMC, Taiwan Semiconductor Manufacturing Corporation, is the global leader in it. Taiwan is the hub of semiconductor manufacturing. TSMC is their UMC is their company, and their company is called Global Foundries, which is actually AMD. It was a very famous company making microprocessors and fabricating them themselves. But a decade or so back, they spun off their manufacturing wing by the name of Global Foundries. It was bought by Abu Dhabi Technology Investment Corporation. They also bought Chartered Semiconductor from Singapore. And recently, about 3 4 years ago, they bought the fabrication business of IBM as well, and they formed this company called Global Foundry, which is currently the number two player in the world of pure play semiconductors. But again, this is a very capital intensive business since the Abu Dhabi Technology Investment Corporation have petrodollars, they can afford it, but it is not for someone who does not have some deep pockets. Uh, Fabulous company. Apple, as a case in point, at one point in time had about $750 billion in cash, more than the US government. But they have never tried to venture into the fabrication business. Why? Because, as they say, the proverbial beef, where lies the beef? Where is the beef? So, actually, all the money that you can make is lies in the fabless thing. It's in the design that the money lies. And the barrier to entry is low. All you need are some good tools and good brains, and you can make it. So Qualcomm and Broadcom have become number two and number four semiconductor companies in the world. I think these rankings change very quickly, so they are no more than number two and number four, but they are still in the top 10 companies in the world. Another hybrid sort of model is fab-like companies. You see, um, when you have outsourced all the manufacturing, you are on a risk that if the company for any reason did not provide you with the capacity and with all the production, then your customers are going to suffer and the company will have a backlash. So one idea is to have, instead of going completely fabless, have a small fabrication plant, fabrication facilities within your own company. So if there are any peak demands or if there is any sudden loss in supply chain, then still you can manage some sort of thing. But is it viable? The jury is out. It's still something companies are experimenting with. So these are the top semiconductor companies in the world. Samsung has recently overtaken the crown of the biggest semiconductor company in the world from Intel. TSMC, the pure play semiconductor king, is number three overall. SK Hynix is actually the Honda semiconductor wing. So it has number four. You can see Broadcom and Qualcomm right there at number six and seven. Nvidia again is a fabulous company, and we see it now in top 10. These are the latest figures as of March 2020. And largest semiconductor companies by revenue, you can see Samsung is absolutely a giant with almost a 44% share, and Intel is second with a 15% market share, and then there are other companies as well. So this is just to give you the idea, and you must be aware of these companies' existence and their businesses. So I always say, please do not take these courses, especially my AIC course, as something of a pure pedagogical value to get some good GPAs. GPAs, hopefully, you'll get a good GPA, but try to get the exposure that I'm trying to convey of the real field of what is happening in the real world. It's very important that you are able to connect this knowledge with the market. Anyway, so there is an interesting service which is called MPW, Multi-Project Wafer Run. So this service fulfills a very important gap in the market. You see, for several universities and developing countries like us, if we want to venture into the market of IC designing, how can we work? Because the costs are very high, we cannot afford our own fabrication plant. And even if we want to send our design to TSMC, let's say, then one lot of design it contains millions of ICs or maybe thousands of ICs. It will cost us very, very dearly. So what can we do? So it's actually a pooling service. MPW service providers are the pooling service provider. So let's say we are sitting in Pakistan, we have made an IC design and we want to get it fabricated. So what we will do is we will contact a multi-project wafer run service and send them our design. The multi-project wafer run service also contact other small companies, startups, and other universities. So for instance, they get one design from Pakistan, one design from India, another design from Israel, another design from a small startup in South Africa. What they will do, they will combine all those designs together into one big design and send it for fabrication to a foundry. And let me tell you, it's somewhat similar to what we do for a PCB fabrication. So consider, just have an example of a PCB fabrication. You can collect different designs of PCB and make a big PCB. What will happen once it is fabricated? Once it is fabricated, it is sent back to the multi-project wafer and service provider, and then it cuts and packs and send it to everyone who is involved in that. So the cost of the IC designing now is being shared among all these interested parties, and hence the total cost of ownership is reduced substantially. So this is the model which helps us to get an IC design in a few years. It will take still a few $1,000s. So you see, cost-effective ASIC design is about $3 to $4 billion at least. And we don't have the capital. In fact, we do not have the expertise to do it. Pure play semiconductors, we can get it from there. But just to give you an idea, a 65 nanometer ASIC, that's a 15 years old technology. The mask set, I'm sure Dr. Ross will teach you about the IC fabrication, and then you will understand about the mask set from there. So a mask set is required for each and every IC that is being designed. So once you need have a mask set, only then you can produce multiple copies of the design. It costs about 1 million US dollars. So multi-project wafer run solution companies come in, and they will cost you like $15,000 for a 2 millimeter by 2 millimeter design and 630 CMOS process. However, if we are just an undergrad and want to have the taste of it, we can do a 2.2 millimeter design on 1.2 micrometers technology, which is pretty old, but the cost is just $130,000. And I think it is something which is manageable from your own pocket for your FYP, or better still, there is National ICT Grassroots Initiative. From there, even you can get it funded if you are into IC designing, and it would be wonderful to have an FYP with a claim that they have designed their own IC. So this is what is achievable and doable. So these are some of the companies that provide MPW services. There is CMP in France, the CNC in Canada, Europractice for the European Union, Cellterra, Malaysia, and Moses in USA. And we have already agreement with Soltera and Moses for sure. So we can get our ICs fabricated, and we have been doing so for the last 8, 10 years or so. So the question comes in, okay, are there any prospects of IC designing in Pakistan? Well, yes, there are prospects, and always I have some more stories to tell you about. For instance, uh, IC designing, we talk about the digital as well as the analog. The digital design is being done at Islamabad, some companies in Lahore, and even in Karachi. There are design houses for digital IC design. And recently, there is a company that has entered into the Pakistani market, and they have established a design center in Lahore, and they have a very lucrative offer. They have an online test. If you clear that test, you will be enrolled in an IC design training program. And if you clear that IC design training program with a 90% mark, we guarantee you will job in China or South Korea or in Pakistan or US or Malaysia at very competitive rates. So this company is called Nr1, and this company is offering this special prospects for this region. And it is actually a startup of an alumnus of Nr University. You might have attended or heard about it. Its seminar was held at Nr University back in November 2019. So by using that, this is an interesting prospect. And what they are doing is they are designing a processor in competition with uh, ARM processors, which are by far the most popular processors for mobile phones right now. But they are coming up with an open architecture. It's called RISC-V architecture. This is what they are offering. This is again, that's something wonderful, which has developed just in a year. A year ago, this opportunity was not there. There are companies working in Karachi, in Islamabad, and Lahore who are producing analog and RF designs. There are many, uh, you may say, veteran engineers of Pakistani origin sitting in the Silicon Valley who have their design centers here, and they hire people and get their ICs designed from here. At the university level, NUST is doing some wonderful work. We have a very good group at Lahore, LUMS. Some friends at PF Keat in Karachi, Dr. Arslan Javed's group is doing a very good work there. Even at ND University, we have the Electronics Design Center, where we have all the tool and testing facilities. And we have been designing ICs for some time for different funded projects and research. At present, we have about 4 PhDs exclusively in IC designing. In fact, analog and radio frequency IC designing at Nr University. And I think we can say that it is the biggest concentration of IC designers PhD in Pakistan. I know 4 is a small number, but these things are growing. And with the passage of time, every time I talk about it with a new batch, there are more stories to tell. So this is about the introduction of semiconductor industry and about its process in Pakistan. If they have any questions, please feel free to ask. It's better to note them down and ask me in this session that we'll conduct. Okay, have a good time. Goodbye.